Look at the towering vertical scale of these pillars. They are supporting a heavy gantry crane and thousands of tons of solid material. The sheer bulk of modern infrastructure involves weights that are difficult to even conceptualize. When you are dealing with loads this massive, you need a material that can survive a very specific physical force: compression. In basic physics, compression is simply the force of being pushed or squeezed together, and concrete is the undisputed champion at absorbing it. The mechanics at work here are straightforward. Imagine the endless traffic of a major highway pushing straight down on these columns. The densely packed atomic structure of concrete pushes back, refusing to yield under the pressure. If physics were perfectly simple and sheer downward compression was the absolute only force acting on a structure, pure concrete would be a flawless building material. But in the real world, weight rarely just pushes straight down. The physical dynamics shift entirely when you move from a vertical pillar to a horizontal span. When a material has to bridge an open gap, the way the weight distributes changes drastically. Think as a heavy load pressing down directly on the center of a bending beam. The top edge of that beam gets squeezed together. That's compression. But because the beam is bowing downward, the bottom edge is actually forced to stretch apart. This diagram shows opposing forces inside a bending span. The top edge compresses, but the bottom edge stretches, creating tension. Here is concrete's fatal flaw. It's incredibly brittle. It has practically zero tension resistance. The moment you pull it apart, it snaps instantly. Because of this brittleness, a horizontal bridge made out of pure, unreinforced concrete would literally tear itself apart under its own bending weight. To build the spans we rely on every day, engineers needed to find a hidden solution. To safely bridge these massive urban gaps, scientists had to find a partner material that explicitly thrives under extreme stretching. To evaluate materials, engineers rely on two vital textbook metrics. The first is stress, the internal force actively trying to tear a material apart. The second is strain, the physical deformation or actual stretching that results from that force. This formula is the physics scorecard for a material's elasticity. Dividing stress by strain gives Young's modulus. A high modulus means enduring immense internal stress while exhibiting nearly zero strain. As the chart indicates, pure concrete scores terribly on this scale. Young's modulus serves as the engineering filter required to find a material that can neutralize concrete's greatest vulnerability. The material that scores perfectly on that elasticity scorecard is something ubiquitous in modern construction: steel. Steel holds a massive mathematical advantage in tension. It boasts a Young's modulus of lastly 200 billion pascals. In physical reality, that massive number means pulling on a length of steel is like pulling on an unbreakable tether. It absorbs extreme force without yielding. Steel is the exact mathematical counterweight to concrete. It thrives under immense tension, perfectly mirroring the way concrete thrives under heavy compression. Let's step out of the textbook physics and back into the actual physical construction of the giant infrastructure we rely on. This shows the hidden reality inside a beam. Before a single drop of concrete is poured, crews assemble a dense skeleton of steel rebar. The manufacturing process requires workers to carefully tie this high Young's modulus steel framework in place and then encase it entirely within high compressive strength concrete. Once the mixture cures, it becomes a distinct hybrid material known as reinforced cement concrete, or RCC. The resulting RCC combines two opposing physical extremes into a single, unified structure. Inside a living structure, there is a real-time synergy at work. The concrete shell acts as an unyielding shield, absorbing all the downward squeeze coming from the traffic above. Simultaneously, that hidden steel skeleton acts as the unbreakable tether. When the span bends and the bottom edge gets forced into tension, the steel grabs hold and prevents it from tearing apart. Look at this completed metro track suspended over an everyday street. This is the finished product of those two exact forces working perfectly in tandem. The massive infrastructure defining the modern world is a carefully engineered environment. It is a hidden, continuous tug of war, perfectly balanced by the laws of physics.